neutron stars are slightly lighter. So they are still ultra, ultra dense, dead stellar cores, but they're not quite as heavy as black holes. They might be sort of 2 times the mass of the sun. Okay. And these 2 objects are relevant to our story today because they're so big, so heavy. Sorry, I should clarify that. They are so heavy, but they're not so big. So they're actually quite compact objects. And that means they're really, really dense. Lots of mass packed into a really small volume. And that means that, remember we said that massive objects bend space-time, that any special effects in Einstein's theory are going to be really pronounced for these objects, right? Because they've got so much mass in such a small region. Okay, so that's why they are the place that we look to when we look for kind of effects of Einstein's theory. Okay, so to understand what these objects do to space, we have a little demo for you. So stars very often live in pairs, what we would call a binary, and they'll spend millions of years happily orbiting around each other stably. And once both those stars have died, have used up their fuel, they can both collapse to form these objects. So you can end up with a pair of black holes or a pair of neutron stars, or you can have the mixed case. You can have 1 black hole and 1 neutron star. And those dead stellar cores will carry on orbiting each other. And so what we want to do now is demonstrate what's going to happen to our space-time here when we have these objects orbiting each other. Dan here is going to help me out. And I should say we've also had some help with this demonstration from Stephen Mould, who created it originally. Now, what we've got here is a drill with a special piece on the end. So it's got these 2 wheels here, which is going to be our 2 black holes or our 2 neutron stars. And Dan is going to use the drill to make them spin, so orbit in our space-time. Now, when we use a drill, the orbit is going to be very fast, okay? It's going to be too fast for us to see. So what we're going to do is we've got a strobe light here, and that's going to enable us sort of to make it kind of look like things are in slow-mo, right? Just by using the frame rate so that you'll actually be able to see what's happening to our sheet of space-time here. Okay, it's going to be quite noisy, so I probably won't attempt to talk over it. But when you're ready, Dan, take it away. Okay, can you see we get these ripple patterns coming out? There we go. Oh, almost, there we go. So we've got our system orbiting, and we're getting this spiral pattern coming out of the center and propagating out to distances. All right, fantastic. Thank you. Okay, so hopefully you all saw that kind of spiral pattern start to emerge. Okay, here it is again. So we've got our orbits going around each other, and much like ripples, when you throw a stone into a pond, there's this pattern that travels outwards. So these ripples, these waves, are gravitational waves. And they have that name because they are ripples in the fabric of space and time itself. So they are ripples in the fabric of space that is the same thing that gives us gravity. Okay, that's why they have that name. Okay, so that's what gravitational waves are. Now, this little video here isn't quite accurate because in this video, the objects just go round each other forever. That's not what happens in nature. What happens is, as those objects orbit around each other, they take energy away from the system with these gravitational waves they're emitting. And that means the objects will start to get closer and closer, and they'll get so close that eventually they will touch, and then they will merge. So our 2 black holes will basically cannibalize each other and form a single big black hole. Okay, and there's something similar happens with the neutron stars. So I've got another video showing you that. Okay, so this time they're going to eat each other. This is what we call in-spiral and merger, the technical terms. And I want you to watch what happens to the fabric of space-time around them as they get closer and closer to that moment of merger. Okay, so here we go. Can you see the waves are starting to get bigger? Okay. So, as they get closer and closer, the waves get larger and larger, and they actually get faster and faster as well. And then they merge, they form that single black hole, and then everything settles down. Once you've got to a single black hole or neutron star sitting there, that doesn't emit gravitational waves. You need this special pattern of two objects going around each other to shake up space-time in this way and produce gravitational waves. So this gives us two really useful things. We found the best place to go looking for gravitational waves. We said it was those really massive objects, right? Black holes and neutron stars. And actually now we've seen that there's a characteristic signal we can go look for. That gravitational waves should get louder and louder, faster and faster, and then they should die away in those last moments before the black holes merge. So how do we detect them? Well, you can't detect them with a regular telescope because they're not made of light. So you need a very, very special piece of kit. So special, in fact, there are only 5 of these in existence in the world right now. There is a 6th one under construction there in India. Okay, what do these detectors look like? Well, they're huge. Here are photos, aerial photos, of the 2 detectors in the USA. This pair are called the LIGO detectors. That stands for Laser Interferometer Gravitational Wave Observatory. And they're on opposite sides of the USA. So this one's called Livingston. It's in Louisiana. The one in the top left is called Hanford. It's in Washington. Washington State, that is. And the reason they're on opposite sides of the USA, that's not accidental. It's so that they're really independent of each other. And so if they both see the kind of same signal at the same time, that's an extra bit of verification for us that it was something that came from outer space. It wasn't, an earthquake or something like that. Okay, and you can see these detectors have these huge, great tubes coming out of them. We call them arms. And they're 4 kilometers long. And each detector consists of a pair of 2 arms at right angles. Usually we can't get the second arm fully in the photo because they're too big. And where those arms meet, there's obviously some kind of building, there's something happening. Okay, so what's going on here? Here is a cut-down version of what's going on. So what happens is somewhere in that building, we shine a very high-power laser at something called a beam splitter. That's the diagonal object in the middle. And that beam splitter chops that laser beam into 2 identical copies. And we send those 2 copies of the laser beam off down these 4-kilometer-long arms. They bounce off mirrors, special kinds of mirrors, at the ends, and they're brought back together. And we add those laser beams together, we say we interfere them. Okay. So, light is a wave, or at least you can often think of it as a wave. And so the default setup of the detectors is such that when we bring those 2 laser beams back together and we add them, we can think of adding these 2 waves. And in the default setup, when there's no gravitational wave present, everything's arranged such that the peak of one wave sits over the dip, the trough of another wave, and so the 2 waves, when added, cancel each other out. And that means we don't get any light out at the final detector here. Okay, we call this destructive interference. What's going to happen when a gravitational wave passes through is that it will change the length of these arms. So, I am a gravitational wave detector. A gravitational wave is going to come at me face on. And by the way, gravitational waves will pass straight through you. They'll pass straight through the detector, straight through the Earth, out the other side, and keep on going. Okay, but what happens is that gravitational wave causes the length of one of my arms to temporarily shrink just a little bit. Obviously, I'm going to exaggerate here. And it will make the other arm stretch a little bit. And then, a short while later, it's going to reverse the pattern. So it will shrink this arm and stretch this arm. And that pattern will alternate backwards and forwards. So this is the gravitational wave detector dance. Okay, I'm told all the kids are doing it on TikTok. Okay, so why does that matter? What happens when the lengths of those arms change is that our two light waves in our laser beams get shifted past each other. And now we can have a situation where the two peaks, the red and the blue there, are in sync. And that means the light beams add together. We call this constructive interference, and you get light coming out. Okay, so light reaches the detector. And the precise pattern of this light, how it changes over time, tells us things about that gravitational wave that passed through. Now, what blows my mind every time is the sensitivity that these detectors have to detect gravitational waves. Because these waves are coming from millions, if not billions, of light years away. By the time they reach us, they're absolutely tiny. So these detectors can detect a change in arm length 1/10,000th the size of a proton. I mean, if you thought atoms were small enough, and a proton is about a factor of 1,000 smaller than that, a proton is a particle that sits in the nucleus of an atom, so 1,000 times smaller, and then 1/10,000th of that. I mean, it is just mind-blowing. Okay, and that's why you don't feel gravitational waves passing through you, because if they do pass through you, the changes they would cause in your body are just so much smaller than kind of all the other things going on inside your body anyway. Okay, so you can't feel them. So these are incredible bits of kit, incredible bits of engineering, and it took decades of work, but we did eventually have our first detection on the 14th of September, 2015. And we give these detections their sort of signature call signs. So they all have a name. They get called GW for gravitational waves, surprisingly. And then the numbers after it give the date of the detection, but sort of backwards. So you have to read it backwards. So it's the 14th of September, 2015. Okay, I have another little movie, which is a simulation of this first event. What you're going to see are two black holes. So this was a black hole binary merger. And you're going to see lots of sort of orange patterns coming out of it. And those orange patterns are the patterns that the gravitational waves make. Okay, and you'll see they make some really kind of beautiful patterns. So these are not just artists' impressions, these are the kind of real structure. Okay, is this going to load? Good. So here we're zoomed out, but you can see the gravitational waves already. Okay, and here are our black holes, and the green regions are showing the regions where space is most strongly distorted. Okay, now look at these kind of helixes. Okay, and away they go. So we've seen that pattern several times now before, this kind of really intense burst of gravitational radiation, and then they're settling down. Okay, that was the first detection. I don't think I can put into words for you how exciting it was to be, sitting in a physics department and, someone comes and knocks on your door and says, have you heard the news, right? They've detected these things for the first time. It's incredible.